Right now, the universe is expanding faster than light, not in one place, but everywhere. Yet most people assume the observable universe is the universe itself. It isn't. The observable universe isn't bounded by walls or edges. It's bounded by time. It's the region of space whose light has had time to reach us. Beyond this horizon, space doesn't suddenly end. What ends is our ability to see. There may be vast regions of reality beyond our view, and that single limitation reshapes how we understand the universe's true scale. By the end of this video, you'll understand what observable really means, and why the universe is far larger than intuition can handle. If you're ready to go deeper into this mystery, hit that subscribe button, and together, let's drift into space. We've been taught a comforting sentence, that the universe is everything. But then we add one small word, quietly, almost politely, observable. And suddenly, the universe we talk about collapses into something smaller. Not because space ends, not because the cosmos has a wall, but because we do. Because we are made of time. Because we are trapped inside a single moment, on a single planet, watching a sky that only shows what it's allowed to show. And what makes this truly unsettling is, the observable universe is not the universe. It's the part that has managed to reach us, the part that has survived the long dark and arrived, thin and ancient, at our eyes. But then the question fractures open. If we can only see what reaches us, what does observable actually mean? And what, exactly, is hiding behind that word? Before we expand the scale, before we speak in billions of light years, before we try to comprehend distances so large they turn our minds into fog, we need to do something most people skip. We need to define the rules of the game, because the universe does not reveal itself to us the way a room reveals itself when we turn on a light. Space is not a place we stand inside, looking around freely. Space is a story told through messengers, and there is only one messenger that reaches us from the deep cosmos with clarity. Light, not as poetry, as physics. Light is how we get our evidence. Light is how we get our truth. And that truth comes with a limit, one that no rocket engine, no future technology, no civilization, no matter how advanced, can negotiate. This is not a human limit. This is a universe limit. And it begins with a simple, uncomfortable idea. We don't see space, we see time, but that creates a bigger problem. Because if observation is time limited, then the universe we talk about is not the whole universe at all. It's a horizon, a cosmic shoreline, and beyond it, we don't have darkness. We have silence. When we say the universe, we mean the totality of reality. Everything that exists, whether we can detect it or not. But when scientists say the observable universe, they're being careful. They're drawing a circle around what we can confirm, not what we imagine, not what we hope, not what might be out there, only what has had enough time to send a signal to us since the universe began. So the observable universe is not a claim about what exists. It's a statement about what we can reach with evidence. That's why astronomers at places like NASA, ESA, and major observatories don't speak in certainties beyond the data, because the cosmos punishes overconfidence. Here's the strange part. The observable universe is not the part we've looked at with telescopes. It's not the part we've photographed. It's not the part we've explored. It's something deeper. It's the volume of space from which any information at all could have reached us at the maximum speed the universe allows. And that speed is not a choice. It's built into reality. Which brings us to the next rule, and it's the one that makes everything feel colder. We tend to talk about the speed of light, the way we talk about speed limits on roads, like it's something we might overcome with better engineering. But Einstein showed us something far more severe. The speed of light isn't just how fast light travels, it's how fast cause and effect can travel, how fast information can travel, how fast the universe can respond. If something happens on a distant world, an explosion, a star collapsing, a galaxy igniting, that event cannot arrive here instantly, not because we lack instruments, but because reality refuses to deliver it faster. Even Stephen Hawking, when describing black holes and cosmic boundaries, returned again and again to the same haunting theme. Physics is not just a description of nature, it's a set of locks, and light speed is one of the strongest locks we know. So when we look into space, we are not scanning a map, we are receiving messages. And every message has a travel time. This means our view of the cosmos is delayed. Always, no matter what. And this delay is not small. It is the reason Observable exists at all. But then another contradiction appears. If light is fast, unimaginably fast, why isn't the entire universe observable by now? Why isn't the sky filled with the full reality of everything that exists? Because speed is only half the story. The other half is time. When we talk about distance, we instinctively think in space terms. Kilometers, miles, across a city, across a continent. But the universe forces a different kind of measurement, because in space, distance is also a delay. The farther something is, the older its information is when it reaches us. So the true limitation is not that galaxies are too far away, it's that their light has not had enough time to get here. And the universe has only had a finite amount of time to exist. That's the rule. If the universe has been around for a certain number of years, then light can only have travelled a certain maximum distance since the beginning, which means there is a region of the cosmos whose signals have reached us, and a region whose signals haven't. Not yet. Maybe never. This is why observable is a time concept wearing the mask of a space concept. And this is where our intuition begins to break, because we want to picture ourselves in the centre of a sphere, looking outward, as if space is simply sitting there, waiting. But space is not waiting. Space is moving through time with us, and everything we see is arriving late. Even the light of the sun is delayed by minutes. Even the face of the moon is delayed by more than a second. In daily life, we don't feel it, but in deep space, that delay becomes the entire story. And now we can say something that sounds almost philosophical, but is brutally scientific. We do not see the universe as it is. We see the universe as it was, and that creates a new problem. Because if we only see the past, then the observable universe is not a boundary in space, it's a boundary in time. Imagine this, we're standing on a beach at night, there's thick fog, and we're holding a flashlight. The flashlight beam cuts into the fog, but only so far. Not because the beach ends, not because the ocean stops, but because the light gets swallowed by the haze. Now replace the fog with time, replace the flashlight with the speed of light, and replace the shoreline with the universe itself. The observable universe is the lit region, the circle of visibility. Not a wall, not a border, just the farthest point where the beam has had enough time to reach and return to us as information. Beyond that, there may be more beach, more ocean, more world, but it's not visible to us yet, and we can't force it to be. Because the fog isn't a material, it's the age of the universe itself. But the universe had one more twist, because this visibility circle doesn't stay fixed. It changes as time moves forward, and that leads us to the most important definition of all. A boundary is something you could, in principle, reach. A wall, an edge, a final line. A horizon is different. A horizon is a limit created by perspective. It's the line where visibility ends, not reality. We already know this from Earth. The horizon at sea isn't the end of the ocean. It's the end of what our eyes can receive from our position, and the cosmic horizon works the same way, except on a scale so vast it becomes emotionally violent, because the cosmic horizon doesn't care how curious we are, it doesn't care what we dream, it doesn't care how advanced we become. It's written into the structure of space-time. The observable universe is the region of space that can be connected to us by light or any causal signal since the beginning. That's why scientists use observable with restraint. It's not pessimism, it's discipline. Because beyond that horizon, we don't have data, we don't have measurements, we don't have confirmed reality. And in cosmology, that difference matters. This is why the word observable is not small. It is the universe admitting something humbling. There are limits to what we can know directly. But here's where the story cracks open, because we have not just a limit, we have a clock. And that clock tells us something about the age of the cosmos itself, which means the next step is unavoidable. If observation is constrained by time, then we must confront the one number that controls everything. How old is the universe? And if you pause right now and look up at the night sky, you're not seeing a scene. You're watching a layered archive, a stack of ancient messages arriving at once. Some are minutes old, some are thousands of years old, some are millions, and the deeper we look, the closer we get to the beginning. But that's not the whole story, because to understand what observable truly means, we have to understand how scientists measure cosmic time itself, and why light travel time becomes the ruler of reality. So now we have the rules. The universe may be everything, but the observable universe is only what has had time to reach us. Light speed is not a technological problem. We can't outbuild it. Observation is constrained by time, not distance alone, and the observable universe is a horizon, not a boundary. But then the deepest question remains, waiting like a shadow behind the numbers. If our cosmic horizon is controlled by time, how do we know the age of the universe at all? What evidence lets scientists speak about billions of years with confidence? And what is the oldest light we can possibly see? The final, faint glow that marks the edge of our vision, because that's where the scale stops being an idea and becomes a measured consequence of physics. And once we touch that oldest light, everything about distance is going to start behaving differently. We keep saying it like it's simple. The universe is about 13.8 billion years old. But how does anyone know that? No one was there to watch the first second tick by. No one can rewind the cosmos with their hands. And yet, astronomers speak about the universe's age with the calm confidence of people reading a clock on the wall. So here's the uncomfortable question beneath everything we're about to measure. What if the universe's age isn't just a number, but a limit on what reality can ever show us? Because the moment we accept the universe has a finite age, we accept something colder. Our vision has an edge, not because we lack power, but because the cosmos hasn't had enough time to deliver the evidence. And that brings us to the rule that silently governs all astronomy. Light is not just illumination. Light is the universe's courier, and it never moves faster than its own speed limit. To understand the scale later, we need the foundation now. When scientists estimate the universe's age, they don't guess. They triangulate, using independent lines of evidence. One of the strongest is the cosmic microwave background, a faint glow filling space, measured by missions like WMAP and Planck. NASA's WMAP work describes it like running the cosmic clock backward, using the patterns in that ancient light and the physics of general relativity. ESA's Planck results tightened those estimates and pointed to an age of about 13.8 billion years as well. This matters because the cosmic microwave background isn't just data, it's a timestamp, a fossil signal, left behind when the universe first became transparent enough for light to travel freely. So we're not measuring age the way we measure a tree's rings. We're measuring age the way we measure a distant storm, by reading the light that finally reaches us and asking what kind of universe could produce it. But then the story gets stranger, because even if we know the age, we still face a brutal constraint. Light moves at about 300,000 kilometers per second, around 186,000 miles per second. In 1 second, light can circle Earth about 7 times. By definition, the speed of light in a vacuum is exactly 299,792,458 meters per second. That's not just a fact for textbooks. That number turns the entire universe into a time machine. NASA explains it in the simplest, most unsettling way. When we look far away, we are seeing objects as they were in the past, because light takes time to travel. So distance isn't only distance, distance is delay, and that means visibility becomes a question of time, not eyesight. Imagine this: we're standing at our front door and we hear a knock. A letter has arrived. No return address, no date on the envelope, but we can still learn something. We can read the paper, we can study the ink, we can measure how weathered it is. And then we realize something chilling. This letter was mailed long before we were born. That's what starlight is. Light is mail from the past, sometimes from a past so deep that Earth hadn't even formed yet. And this is why the age of the universe matters so much, because the age tells us how long the mail has been traveling. To feel the speed of light, we have to bring it down to a human scale. NASA points out that even the Moon, our closest companion, is seen slightly late. Light takes about 1.3 seconds to reach us from the Moon. Neptune, still inside our own solar system, sits so far out that its light takes about 4 hours to arrive. Now stretch that outward. If light is the fastest messenger allowed by physics, and even it takes hours to cross our neighborhood, then what does 13.8 billion years really imply? It implies the universe has only had 13.8 billion years worth of message delivery time to show us anything at all. And this creates a bigger problem. If the universe is older than everything we've ever built, then most of what exists may be forever outside our reach, not because it's too far, but because the message has not arrived, and some messages never will. Here's the strange part. When we say a galaxy is 10 billion light years away, we're quietly saying something else. We are seeing that galaxy 10 billion years in the past. We are not watching it as it is now. We are watching what it was when the light began its journey. So the deeper our telescopes go, the more the universe stops looking like a place and starts looking like a timeline. Hubble's deep fields didn't just show faint galaxies, they revealed that space itself is layered with ancient eras, stacked on top of each other in light. And this is why our instincts fail, because our eyes were built for immediate worlds. But astronomy is not immediate. Astronomy is delayed truth. Now let's anchor 13.8 billion years to something we can feel. The universe's age is so vast that it dwarfs every human calendar. When the cosmic microwave background was released, when that ancient light first began traveling, the universe was only about 380,000 years old. At that time, there were no stars, no galaxies, just a hot, dense, early cosmos cooling into transparency. Now compare that to Earth's story. Earth is about 4.5 billion years old, meaning most of the universe unfolded before our planet even existed. When dinosaurs walked the Earth tens of millions of years ago, most of the cosmos we can see today was already ancient beyond imagination. So when we stare at deep space, we're not just looking at far. We're looking into a time so old our world had not yet earned its place in it. And that realization changes the emotional weight of the night sky. It isn't merely beautiful, it's historical. It's filled with light that has been traveling longer than anything we've ever been. Now, we reach the hard edge of visibility. The oldest light we can directly observe is the cosmic microwave background. NASA describes it as a heat signature left by the Big Bang, seen by missions like COBE and WMAP, dating to about 380,000 years after the Big Bang. Harvard and Smithsonian calls it the oldest light in our universe, a snapshot from when the cosmos was about 380,000 years old. And NASA's visualization work describes Planck mapping that ancient light around 370,000 years after the Big Bang with extraordinary precision. But what does it mean? It means there was a moment when the universe changed state. Before that moment, the universe was like a blinding fog, light constantly scattered by charged particles. After that moment, the fog thinned, atoms formed, light finally traveled freely, and that first free-traveling light is still arriving now, washing over us from every direction like a cold, ancient tide. This is why the cosmic microwave background is not just another image, it is a wall of time, a surface we can measure, but not see past. And this wasn't the only twist, because once we understand that the oldest light began its journey when the universe was only a few 100,000 years old, we're forced to confront how strange distance becomes when time and expansion enter the picture. Now place yourself inside this reality. You stand beneath a quiet sky, cold air, stillness, a faint shimmer of stars. But what you're seeing isn't a portrait of the present. You are surrounded by late arrivals. Some light started traveling before Earth existed. Some began before our species ever appeared. And even the moon, the closest world you can point to, is already slightly behind itself when you see it. So the sky doesn't just contain distance, it contains time, delivered to us at the fixed speed of light. That's when the emotional weight lands. We live inside a bubble of received history. We don't witness the universe as it is. We witness what the universe has had time to tell us. So here's what we've built, piece by piece. The universe has a measured age of about 13.8 billion years, supported by CMB-based missions like WMAP and Planck. Light has a strict physical speed limit, defined exactly and obeyed everywhere in vacuum. Looking farther means looking deeper into the past, because light takes time to cross space. The oldest light we can directly see is the cosmic microwave background, released when the universe became transparent around 380,000 years after the Big Bang. This is the foundation that makes scale possible, because once we accept that we only see what time allows, then the next question becomes unavoidable. If the universe is 13.8 billion years old, why does the observable region end up so much larger than 13.8 billion light years? That should be impossible, and yet it's real. But then, everything complicates, because the universe doesn't behave like a static stage where light simply crosses a fixed distance. Space itself changes while the light is traveling, and that means our intuition about distance, our simple miles and kilometers thinking, starts to fracture. In the next stretch of this journey, we confront the paradox head-on. How can we see galaxies whose light has been traveling for most of cosmic history, and yet those galaxies are now much farther away than that travel time suggests? Here's where the story cracks open, because distance in space is not what it seems. And once we understand why, the true scale of the observable universe stops sounding like a number and starts sounding like a consequence. We like to think distance is honest, a straight line from here to there, a number we can trust. But then we point our telescopes into deep space, and something breaks. We find galaxies so far away that their light has been traveling for most of cosmic history. And yet those same galaxies are now so distant that by our everyday logic, light should never have been able to reach us at all. It feels like reality is cheating, It feels like the universe is bending its own rules. But this is where everything changes. Space is not a silent stage where objects move. Space is an active ingredient. It stretches, it expands, and it makes distance behave like something almost alive. So if we want the true scale of the observable universe, we have to accept one uncomfortable fact. Distance out there is not what it seems. When we picture motion, we picture this: a ship crossing an ocean, a car moving down a road, an object travelling through space. So we assume galaxies recede the same way, like they're fleeing from us into the dark. But astronomers don't describe the large-scale universe that way, because on the biggest scales, galaxies are mostly not flying through space. They are being carried by something stranger, the expansion of space itself. This isn't wordplay, this is general relativity, the framework Einstein gave us for how space-time behaves when filled with matter and energy. And it forces a distinction that shatters intuition. Objects moving through space is one kind of motion. Space itself expanding is another. If we confuse those two, the observable universe will never make sense. But then a deeper mystery appears, because once we accept that space expands, we run straight into a paradox. Some galaxies can recede from us faster than light, and yet we can still see them. How is that possible without breaking physics? Let's slow down and be precise. When we say nothing can travel faster than light, we're talking about local motion, objects moving through space in a way that would transmit information faster than nature allows. But the expanding universe is not a spaceship accelerating. It's not a galaxy firing engines. It's the distance between distant galaxies changing because the underlying fabric of space is stretching. NASA explains this carefully. Because the universe expands, the relative recession speed increases with distance, and some galaxies can be far enough away that their distance increases faster than light could cross that gap. That sounds illegal until we remember the key word: relative. In general relativity, velocity across cosmic distances isn't the same simple thing as velocity in your neighborhood. Locally, light still wins. Locally, physics remains strict. No signal outruns light in its immediate region. But across the enormous curved geometry of the universe, recession is driven by expansion, by the growth of distance itself. And this creates a bigger problem, because if space can expand like this, then how far away something is depends on what we mean by far, which brings us to the confusion that traps almost everyone. Why do some galaxies appear farther than light could travel in the age of the universe? We already agreed on something fundamental. Looking far away means looking back in time. Light takes time to arrive. So we naturally think, if the universe is about 13.8 billion years old, then light can't have travelled more than about 13.8 billion light years. That sounds clean, except it's incomplete. Because while that light was travelling, space was expanding. The path length itself changed underneath the photon. So the light didn't cross a static distance. It crossed a distance that kept growing. That means two things can be true at the same time. The photon travelled for about 13.8 billion years, and the galaxy that emitted it can be much farther away now than 13.8 billion light years, because space expanded during the journey. This is one reason astronomers distinguish between light travel time and the present-day distance to the source in an expanding universe. And that difference isn't small. It's the reason the observable universe ends up with a present-day radius on the order of tens of billions of light years, not merely 13.8. But here's the strange part. If space can stretch distances while light is in transit, then we need a way to imagine this without turning it into fantasy. So let's do it once. Clearly, simply, and physically. Picture this. We're walking down an airport moving walkway, trying to reach a friend at the far end. but the walkway is moving away from us. Not fast enough to stop us completely, but fast enough to make the trip longer. We keep walking at the same pace. We never break our speed limit, but the distance we still have left keeps changing while we're moving. That's what happens to a photon traveling through an expanding universe. The photon always moves at light speed locally, no exceptions, but the space it crosses expands while it's crossing it. So even though the photon's travel time is finite, the present-day separation between us and the emitter can become far larger than our instincts expect, and once we feel that, the paradox begins to loosen its grip. But then the universe adds another twist. If expansion can make distances grow, could that expansion force galaxies to recede faster than light? Yes. And that still doesn't violate the speed limit. On the largest scales, astronomers describe the universe using a model where space has a scale, an overall stretching factor that changes with cosmic time. That stretching is what we call cosmic expansion, and we see its fingerprints in redshift. Light from distant galaxies is stretched to longer wavelengths as the universe expands during its journey. This is why the same journey can be described in two different but both true ways. The time that light spent traveling to reach us, the present-day distance between us and where that source is now. This is also why astronomers talk about distances like co-moving distance, a way of describing separations in an expanding universe that keeps track of how space has stretched, and it leads to the statement that feels like a cosmic insult. A galaxy can be so distant that its recession due to expansion is greater than light speed. Scientific American has described this exact fact. Galaxies can recede faster than light in an expanding universe, and the reason it doesn't break relativity is that this recession isn't a spaceship moving locally through space faster than light. But now we have to answer the question that everyone feels in their bones. If something is receding faster than light, how can we ever see it? Here is the key. Relativity's speed limit is about local motion through space and the transmission of information locally faster than light. Cosmic expansion is different. It's geometry. It's the way distances are defined across a changing space-time. So when we say a galaxy recedes faster than light, we are not saying it's breaking the rules in its own neighborhood. We are saying that, because of expansion, the distance between us and that galaxy grows in a way that can exceed light speed when expressed as distance per time across cosmic scales. And we can still see many distant galaxies because what we receive is not the light they emit now. We receive light they emitted when the universe was younger, when the separation was different, and when the expansion conditions along the route allowed the signal to make progress toward us. This is not a loophole. It's the universe obeying relativity exactly, just not the simplified, everyday version our minds crave. And once we accept that, we stop asking, how far is it? And start asking the real question, how has the universe expanded during the time the light was traveling? Because that is what turns the observable universe from a simple sphere into something far more haunting. And if you could stand in perfect darkness, away from city lights, looking up, you would be staring at a map that lies in the most honest way possible. Not because the universe wants to fool you, but because your eyes are receiving a mixture of eras, a nearby star that is almost current, a galaxy that is millions of years behind, and in the deep field, light that began its journey when Earth was still young, when early life was still reshaping the planet's atmosphere. One sky, many times, and underneath it all, space itself expanding, quietly stretching the meaning of far. But that's not the whole story, because if expansion is the mechanism, then we have to ask where this idea came from in the first place. Who proved it? How did they measure it? And what did that discovery do to our understanding of cosmic scale? So now the illusion has cracked. Space does not behave like a fixed stage. It expands. Light travels at a strict local limit, but the distance it crosses can grow while it travels. That's why some galaxies can have recession speeds greater than light without violating relativity. And that's why present-day distances can be far larger than the simple age times light speed intuition. But then, the real tension tightens. If expansion is doing all of this, how did we discover it at all? What measurements convince scientists the universe is expanding? How do they measure the expansion rate? And why does that rate reshape distances differently on the larger scales than it does in our local cosmic neighborhood? Because once we understand the expansion itself, we'll understand the mechanism that turns a young universe into an unimaginably vast horizon. For most of human history, the sky felt still. Stars rose, stars set. The cosmos looked like a frozen ceiling. But then, astronomers found something catastrophic hiding inside starlight. A quiet drift, a red stain on the spectrum, a pattern that didn't care what we believed. The universe was expanding, and once we understood that, the true scale of everything shattered, because expansion doesn't just move galaxies, it stretches the meaning of distance, it turns time into geometry, and it turns a young universe into an unimaginably vast horizon. But this created a bigger problem. How did we discover expansion at all? How do we measure its rate? And why does it reshape the distant universe while leaving our local world almost untouched? We can't watch the universe from the outside. We can't stand back and see it swell. So scientists did the only thing possible. They listened to light. They measured how it changes on the way to us. And they looked for a rule. In the early 1900s, astronomers began collecting galaxy spectra, splitting galaxy light into its color barcode. Some of those lines were shifted toward red, redshift, a sign the light had been stretched during its journey. At first, this wasn't automatically expansion, it was evidence, a clue. But then the clues locked together, and the universe began to confess. The breakthrough wasn't just seeing redshift, it was tying redshift to distance. That required a second tool, a way to measure how far away galaxies really are. Astronomers used Cepheid variable stars, stars whose brightness changes in a reliable pattern, making them powerful distance markers. NASA notes that Edwin Hubble confirmed expansion in 1929 using observations including galaxy redshifts, measured by Milton Humason, and distances estimated using Cepheid stars. Then the pattern emerged. The farther away a galaxy was, the faster it appeared to recede. A clean relationship, distance linked to recession. This became the observational backbone of modern cosmology, the Hubble-Lemaitre law, and once that law existed, the universe stopped being a static arena. It became a living system, stretching, thinning, unfolding. But here's where the story cracks open. If galaxies are moving away, are they flying through space like ships across an ocean? Or is something deeper happening? Our instincts want motion to be personal. A thing moves, it travels. But cosmic expansion is colder than that. In expansion, galaxies don't need engines, they don't need a direction. The distance between them increases because space itself is stretching. NASA describes the key fingerprint of this. As the universe expands, it stretches light traveling through it, creating cosmological redshift. So the redshift isn't just a galaxy speeding away, it's also a scar left on light by an expanding universe. And this is why expansion changed everything. It means distance isn't a fixed ruler. The ruler itself grows. Picture this. We place a handful of raisins into rising dough. As the dough expands in the oven, every raisin moves away from every other raisin. Not because the raisins are crawling, not because they chose to run, but because the dough between them is swelling. In this analogy, the raisins are galaxies. The dough is space. The growing separation is expansion. No single raisin is the center. Every raisin sees the others receding. That's the unsettling elegance of it. But then comes the next question. the one that makes expansion measurable instead of poetic. How fast is the dough rising? Expansion has a rate, a present-day pace, measured as how quickly distance increases per unit distance. This is what people often call the Hubble constant, the current expansion rate. NASA explains the modern distance ladder logic behind measuring it. We calibrate nearby distances using geometry, parallax, then use Cepheid variables, then connect them to type Ia, supernova, exploding stars that can be used as bright, consistent distance markers across much larger ranges. So we build outward step by step, each rung tested against the last. We measure distance, we measure redshift, we infer expansion. But there's another path too, one that doesn't start with nearby stars. It starts with the oldest light in the sky. ESA explains that the Hubble constant can also be estimated by fitting a cosmological model to cosmic microwave background observations using missions like WMAP and Planck to infer what the expansion rate should be today. And then there's a third approach, measuring how large-scale matter patterns encode a standard ruler. The DESI collaboration describes baryon acoustic oscillations as a powerful standard ruler used to constrain the universe's expansion history by measuring clustering in the large-scale structure. 3 paths, 3 independent ways of listening to the universe, and they largely agree on the core truth: space expands. But the details, especially the exact expansion rate today, have become one of the most serious tensions in modern cosmology. NASA's own overview describes this Hubble constant tension as different methods yielding values that don't perfectly match, and that tension matters because the expansion rate controls the scale of the observable universe. But now we need to feel what expansion rate actually means in human terms. One common way to express today's expansion rate is, for every about 1 megaparsec, about 3.26 million light-years, distance increases by roughly tens of kilometers per second. A widely used ballpark expression is about 70 kilometers per second per megaparsec, though the exact value depends on the method. Let's translate that into something we can touch. A simplified version often quoted in teaching is around 22 kilometers per second for every million light-years, meaning the farther out we go, the faster the recession becomes. 22 kilometers per second is about 49,000 miles per hour. At that speed, we could cross the entire length of a country in minutes. We could circle Earth in about half an hour. And yet, if we had been moving at that speed since the pyramids were built, about 4,500 years ago, we would have travelled only about 0.33 light-years. Not even 1 light-year. Not even a quarter of the distance to the nearest star. So the expansion rate feels small, almost harmless, when we translate it into human travel. But then the universe reveals the trap. Expansion doesn't act over kilometers. It acts over millions and billions of light-years. Tiny rates applied to vast separations compound into something terrifying. And that brings us to the next rule. If space is expanding, we might expect everything to stretch. Atoms, bodies, solar systems, a slow tearing of reality. But we don't see that. We measure stable rulers, stable orbits, stable atoms. This isn't a contradiction. It's the hierarchy of forces. On small scales, other forces dominate. Gravity holds solar systems together. Electromagnetism holds matter together. On large scales, between unbound galaxy groups and across cosmic voids, the expansion of space becomes the dominant story. A peer-reviewed analysis in the American Journal of Physics frames the key idea. Bound systems do not participate in the general expansion in the same way the large-scale universe does, and the question of what expands is subtle, but the everyday takeaway remains. Local bound structures don't simply swell with the universe, so expansion doesn't erase our neighborhood. It reshapes the deep cosmos. It's like wind across an ocean. Close to shore, rocks stay rock. But across open water, the surface can become a moving world. And this created a deeper mystery. if expansion mainly dominates the largest scales, what happens when it acts for billions of years? Expansion is not a one-time shove. It's a continuous stretching, a quiet compounding. This is why the observable universe becomes so large, even though the universe has a finite age. Because over billions of years, separation grows, again and again and again. We can feel the emotional weight of this if we remember what our telescopes actually see. Light from distant galaxies began its journey when the universe was younger. While that light travelled, space expanded. By the time the light reaches us, the universe has had billions of years to stretch the distance behind it. NASA's explanation of cosmological redshift captures this idea directly. Expansion stretches the light during transit, and the greater the redshift, the farther the light has travelled through expanding space. So expansion doesn't just change where galaxies are, it changes what distance means across time. And now we can say the most important thing this chapter needs to deliver. The scale of our observable universe is not just a result of light speed, it's the result of light speed plus billions of years of expanding space. That is the mechanism. That is the engine. And once we accept it, the next part of the story becomes inevitable. Because to understand scale, we don't just need expansion as a concept. We need to understand how a universe that began extremely small grew into a horizon tens of billions of light years wide. And if you could stand out there between galaxies, where space is emptiest, you wouldn't feel a wind, you wouldn't hear a sound. But over time, you would watch the universe quietly pull everything apart, so slowly that a lifetime wouldn't notice, yet so relentlessly that billions of years cannot resist it. So now we have the mechanism that inflates scale. Astronomers discovered expansion by linking galaxy distances to redshift, turning light into evidence. Expansion stretches light in transit, imprinting cosmological redshift across the universe. The expansion rate is measured through multiple methods: distance ladders with Cepheids and supernovae, cosmic microwave background fits, and large-scale standard rulers like baryon acoustic oscillations. Expansion dominates the larger scales, while bound structures don't simply expand with it. But this is where the story tightens. Because once we accept expansion, one question remains, waiting like a pressure crack in the dark. How did a universe that began hot, dense, and compact become a vast horizon we can't even emotionally hold? To understand that, we have to go back to an early cosmos, smaller than intuition allows, back to a time when the observable horizon itself was still growing. And when we return from that beginning, the size of the universe we can observe today will stop feeling like a number and start feeling like a consequence. Right now, our sky feels enormous, so enormous that our minds instinctively protect us by turning it into an abstraction, a distant backdrop, a quiet ceiling of stars. But then we learn something that changes the entire emotional weight of reality. This vastness wasn't always here. The part of the universe we can observe today, the region that can reach us with light, was once smaller, tighter, hotter, almost unrecognizable. Not smaller by a little, smaller in a way that makes the word beginning feel dangerous. And this is where everything changes. The observable universe is not just a space, it's a history of expansion, a horizon that has been growing, second by second, since the first light was finally allowed to travel. But then, the uncomfortable question appears. If the universe began in an extreme compact state, how did our observable horizon become so unimaginably vast? To understand the true scale of the observable universe, we have to do something unnatural for the human brain. We have to stop imagining space as a fixed container and start imagining space as a thing that evolves, because the early universe was not just the universe, but smaller. It was a different environment entirely, a place where light didn't glide cleanly through darkness, a place where matter and radiation were tangled together, violent, dense, and blinding. NASA describes the early cosmos as dense and tremendously hot, in a state where ordinary atoms couldn't even exist in the same way they do now. Harvard and Smithsonian describe those first hundreds of thousands of years as a hot soup of particles and photons, too dense for light to travel very far. So when we say the universe expanded, we are not describing a simple stretching. We are describing a transformation, a universe cooling, a universe thinning, a universe moving from opaque to transparent, a universe becoming a place where light can finally run, and once light can run, the observable horizon can begin to grow. But that created a bigger problem. If the early universe trapped light, how do we even know what it was like? For a time, the universe was not a clear window. It was fog, not metaphorical fog, physical fog. A cosmic haze made from free electrons scattering photons again and again. Light tried to move and was immediately slammed back into matter. That's why early space wasn't dark the way we imagine darkness now. It was bright, yet trapped. A violent glare that couldn't travel. NASA explains this turning point. Around 380,000 years after the Big Bang, the universe cooled enough for electrons to bind to nuclei. The cosmic fog cleared, and the universe became transparent, allowing light to travel freely over great distances for the first time. And this matters for our story because it defines something chilling. There is a moment in cosmic history when the observable universe truly begins as a meaningful concept, not because the universe started then, but because our evidence can only begin then. That ancient release of light is what becomes the cosmic microwave background, an afterglow still filling the sky today. And notice what this implies. When that light was released, Earth did not exist. The sun did not exist. The Milky Way was still far in the future. We are receiving a message from a time when our world was still impossible. But then the story gets stranger. Even after that light escaped, space didn't stop changing. It kept expanding while the light was traveling, and that expansion rewrote the meaning of distance itself. When that first ancient light began moving, it didn't cross a frozen universe. It crossed a universe that stretched beneath it, quietly, relentlessly. So the photon did something that feels impossible to us. It traveled for billions of years, and yet the distance between us and its origin continued to grow during its journey. That's why the observable universe is not simply the age of the universe in light years, because distance didn't sit still long enough for that to be true. Astronomy.com explains this core idea in plain terms. Because the universe expands, light travels through space that is stretching, and that stretching changes how we describe distances today versus when the light began its trip. So we have to hold two truths at once. Light travel time tells us how far back in time we are looking. Expansion tells us why the present-day separation can be far larger than our intuition expects. And this is where the story cracks open. If expansion was reshaping distances while ancient light traveled, then the observable universe today must be much larger than it was when that light first escaped. But how do we feel that? How do we visualize something that grew while it was being observed? Picture this. We draw two dots on a rubber band. One dot is us. The other dot is a distant region of the universe. Now imagine a tiny ant walking from the far dot toward us. The ant moves at a steady speed. It never accelerates. It never cheats. But while the ant walks, we slowly stretch the rubber band. Now the journey changes. The ant still moves at the same speed, but the path beneath it is growing. So by the time the ant reaches us, the distance between the dots is larger than it was when the ant started. That's what happens to light in an expanding universe. Light keeps its local speed, but the space it crosses expands while it's crossing it, and that expansion inflates the present-day scale of what we can observe. But then the unsettling implication arrives. If the observable horizon grows with time, that means the edge of what we can see is not fixed. It's a moving boundary, a horizon that has been retreating forever. In the early universe, the region we can observe today was once far more compact, not because the universe was cramped inside a container, but because the same amount of matter and radiation was packed into a smaller volume, dense, hot, aggressive. NASA's summaries of early cosmic history emphasize how the universe cooled and became transparent as it expanded, linking expansion directly to the universe becoming a place where light could move freely. So here's the truth we have to carry. When that ancient light was released, it was released from a universe that was dramatically smaller than the universe we measure today. Then, over billions of years, expansion stretched space. So the present-day distance to that surface of last scattering, the source region for that oldest light, is far larger now than it was then. This is not speculation. This is how cosmology converts observed light into a measured history, and this is why our observable universe becomes so vast, because time gives light more reach, and expansion inflates the distance behind it. But now we're forced into the next, deeper idea. Not only did the universe expand, our observable horizon itself has been growing, meaning there was a time when parts of today's observable universe were simply not observable yet, because their light hadn't had enough time to reach us. A horizon is not a wall. A horizon is a limit created by perspective, a boundary created by what signals can reach us. In cosmology, this concept is often described as the particle horizon, the maximum distance from which light could have reached an observer since the beginning, shaped by the universe's expansion history. But we don't need the technical term to feel the reality. We just need to accept what time does. Every second that passes, light has one more second to travel. So the sphere of what can reach us grows, slowly, relentlessly. And this is the emotional gravity of our situation. We are not standing in a universe that is fully revealed. We are standing in a universe that is still arriving. The observable universe is a horizon that expands, not because the universe adds new space for us, but because more of the universe has had enough time to send us its evidence. But that's not the whole story, because the evidence that reaches us is not neutral. It is stretched, aged, distorted by expansion. So what we gain in visibility comes with a cost. We see deeper into time, but never in real time. And if you step outside tonight and you let the silence settle, you can feel it. You're not looking at a distant place. You're looking at a delayed universe, a universe that has been traveling toward you, photon by photon, since long before Earth could even exist. That sky above you is not a scene, it's a shipment, a delivery of ancient light arriving late. And it's still arriving. So now we understand why scale grew. The early universe was hot, dense, compact, and for a time, opaque to light. Around 380,000 years after the beginning, the universe became transparent and light could travel freely. That light has traveled across a universe that continued expanding beneath it. Our observable horizon grows because time keeps allowing more regions to send us information. This is why the observable universe today is far larger than our instincts predict. It isn't just age times light speed, it's age plus expansion compounded over billions of years. And now, we're ready for the moment most people resist. Because the next step is not philosophy, it's a number, a measured scientific number, so large it feels like it should be wrong. We've now seen the mechanism, a small beginning, a long expansion, a horizon that keeps growing. But then the universe demands we face the final question that has been hovering behind everything we've said. How big is the observable universe right now, today, in real distance? Not in light travel time, not in how long the photons have been moving, but in the present-day scale of the cosmic horizon. Because when scientists calculate it, the answer is not what our brains want. And once we say that number out loud, the true scale of the observable universe becomes unavoidable. We're about to say a number out loud that makes the universe feel dishonest. Because we've been careful, we've built the rules, we've accepted light speed, we've accepted time, we've accepted expansion, and still, the final scale of the observable universe lands like a fracture in the mind, about 93 billion light-years across. 93 billion, not the age of the universe in light-years, not 13.8 billion, but a number so much larger that it forces a question with teeth. How can we see a universe that is bigger than the amount of time light has had to travel? This should be impossible. Except it isn't. And the reason is the same quiet mechanism that has been reshaping everything in this series. Space expands while light is in transit. When scientists say the observable universe is about 93 billion light-years in diameter, they are not claiming we can see objects emitting light from 93 billion years ago. We can't. The universe is about 13.8 billion years old, a value refined by measurements of the cosmic microwave background from missions like ESA's Planck. So, the deepest light we observe has travelled for roughly that amount of time. But the 93 billion light-year number is different. It's not a how long number. It's a how far today number. It's the present-day size of the sphere of space from which light has had enough time to reach us since the beginning, accounting for how the universe has expanded during that travel. And this is where everything changes. We are not measuring a static universe. We are measuring a universe that has been stretching the ruler while we were trying to read it. Let's lock the geometry into place. The radius of the observable universe is about 46 billion light-years in every direction. NASA's Jet Propulsion Laboratory even uses this scale as a reference point when talking about the known universe. The diameter is roughly double that, about 93 billion light-years across. This is the central numerical truth of our entire video, and we're going to treat it with respect, because it's not a fun fact, it's the shape of our observational reality. Now we need to answer the only question that matters. How do scientists actually calculate it? We can't point a telescope at the edge and read a distance label. So cosmologists do something more disciplined. They combine what we can measure directly with a physics-based description of how the universe expands. Here's the chain, slow, clear and grounded. They measure the universe's age and expansion history using the cosmic microwave background, light released when the early universe became transparent. Missions like Planck mapped that ancient radiation in extraordinary detail and used it to refine cosmic parameters, including the age, around 13.8 billion years. They use that expansion history to compute the maximum reach of light, how far a light signal could have travelled from the beginning until now, while space itself expands. This is why the observable universe is tied to the universe's expansion story, not just its age. The result is a present-day distance to the edge of our observable region, about 46 billion light-years in one direction, or about 93 billion light-years across. This isn't speculation, it's a calculation anchored to measurements, especially the oldest light we can observe, and the way expansion has unfolded since then. But then, the uncomfortable paradox returns. If the universe is only 13.8 billion years old, why isn't the radius 13.8 billion light-years? Here is the problem, in human language. A light-year is a distance, a year is time. So our instincts fuse them together and assume distance must equal time. But the universe does not allow that shortcut, because while light was travelling for 13.8 billion years, the space it travelled through expanded, so the light didn't cross a fixed road, it crossed a road that kept lengthening behind it. That's why Britannica explains the key idea like this. Light emitted long ago has been travelling for 13.8 billion years, but due to expansion, the matter that emitted it is now much farther away, on the order of 46 billion light-years in distance. So, the 13.8 billion is the travel time, the 46 billion is the present-day separation after billions of years of expansion, and the 93 billion is simply the full width of that sphere. Now we need to make that feel real, not abstract. Picture this. We print a photograph of two people standing a meter apart. Then we print it on a sheet of fabric. Now we stretch the fabric slowly over time. The people in the picture don't move, but the distance between them on the fabric increases anyway, because the material itself is stretching. That's what cosmic expansion does. A photon can start its journey when the universe is younger and smaller, and arrive after billions of years of travel into a universe where the fabric has stretched so much that the origin of that light is now vastly farther away than our instincts allow. The photon obeyed the speed limit the entire time, but the stage beneath it grew, and that is why the observable universe is so large. We should say what 93 billion light-years actually means in distance we can feel. NASA defines one light-year as about 9.46 trillion kilometers, about 5.88 trillion miles. So 93 billion light-years is roughly about 880 sextillion kilometers, about 550 sextillion miles of present-day distance across our observable sphere. And even those words, sextillion, don't land emotionally. So let's do one more translation the human body understands. Even moving at light speed, about 300,000 kilometers per second, about 186,000 miles per second, crossing the observable universe's diameter would take about 93 billion years of travel time. That is more than 6 times the current age of the universe, which forces a strange clarity. The observable universe is not what we can reach, it's what can reach us, and even then, only through the ancient light already on its way. Now let's handle the most common confusion. Radius, about 46 billion light-years, is the distance from us to the edge in any direction. This is what matters when we ask, how far outward can we receive information from? Diameter, about 93 billion light-years, is the full width across the observable sphere. This is what matters when we ask, how large is the observable region as a whole? And there's one more subtle truth hidden inside this geometry. We are not the center of the universe. We are only the center of our observable universe, because every observer, anywhere, has their own horizon based on what light has had time to reach them. So this number isn't a crown, it's a limit, a boundary created by time, light, and expanding space. So what is the edge of the observable universe? Physically, it is not a border, it is not a shell of matter, it is not a place we could fly toward and touch. It is a horizon, the maximum region from which light could have reached us since the beginning, given the expansion history of the universe. It's a quiet mathematical fact turned into a real cosmic boundary. Beyond it, signals haven't had time to arrive, not because nothing is there, but because time hasn't delivered it. And this is why the number has such existential weight. It tells us what portion of reality has had enough time to communicate with us. And if you hold that in your mind for a moment, you realize the edge of the observable universe is not just far away. It's late, it's reality arriving after a 13.8 billion year delay through a universe that kept stretching the distance while the message was still traveling. Now we've delivered the number and the mechanism behind it. The universe's age is about 13.8 billion years, refined by Planck. Observations of the cosmic microwave background. The observable universe is about 46 billion light-years in radius, or about 93 billion light-years in diameter, because expansion stretches space while light is in transit. This edge is a horizon of information, not a physical wall. But then a new question replaces the one we solved, a question with real weight. Because once we know the size of the observable universe, we have to face what that size actually contains. What fills this immense volume? How many galaxies are inside it? What is the large-scale architecture, filaments, clusters, voids? And why is so much of this staggering sphere almost entirely empty? That's where we go next. We've just faced the scale, a sphere almost 93 billion light-years wide, a volume so vast it stops feeling like space and starts feeling like an ocean with no shore. But now comes the unsettling question, because when we picture the universe, we picture stuff. Galaxies like lanterns, nebulae like storm clouds, stars like embers scattered through a dark room. Except that picture is a lie of the eye, because most of the observable universe isn't filled with light. It's filled with absence, and what we're about to learn is quiet, but disturbing. The observable universe is not a crowded city. It's a thin network of islands, floating in an almost perfect vacuum. And once we see what actually fills this immense volume, we'll never hear the word empty the same way again. When we ask what fills the observable universe, we're really asking four things. How many galaxies are inside our observable horizon? How is matter arranged on the largest? Scales, filaments, voids, clusters. What is the universe made of? Normal matter, dark energy. And why, despite everything, is most of it still empty? We're not going to speculate. We're going to walk through what scientists have measured, what missions like Hubble, Planck, and modern surveys have forced into the light, and then we'll translate that scale into human meaning, so we can actually feel it. For decades, a common estimate was that the observable universe held around 200 billion galaxies. Then Hubble's deep surveys changed the situation. In 2016, astronomers using Hubble data argued that the old estimate missed a huge population of faint, distant galaxies, and that the real number could be closer to 2 trillion. 2 trillion. That number doesn't sit in the mind, it slips through it. So we anchor it to something human. If we tried to count them, 1 galaxy per second, without sleeping, it would take over 60,000 years to reach 2 trillion. That's longer than the entire span of recorded human history. And that's just counting the galaxies, not studying them, not understanding them, just whispering their existence into a list. But here's where the story cracks open. Even 2 trillion galaxies don't fill the universe like we imagine. Because galaxies aren't spread evenly like seeds in a jar. They gather, they braid, they form something that looks almost biological. On the largest scales, the universe is arranged in what NASA describes as a twisting, thread-like structure, the cosmic web. Galaxies collect into groups, clusters, superclusters, and vast walls of galaxies, and between these bright concentrations are enormous voids, regions with far fewer galaxies. This isn't decoration. This pattern is the fossil shape of gravity at work over billions of years, matter flowing toward matter, deepening the contrast. The cosmic web is the universe showing us what gravity does when given enough time. But then comes the part most people don't expect. The web is mostly space, not strand. The luminous parts, the galaxies, the clusters, are the highlights. The voids are the majority. Picture this. We're looking at Earth from orbit at night. We see bright clusters of city lights. We see thinner lines connecting them, highways and corridors of development. And then we see vast dark regions, oceans, deserts, mountains. Now scale that image into the universe. The bright cities are galaxy clusters. The highways are filaments, streams of matter where galaxies prefer to form. The dark oceans are cosmic voids, immense volumes with very little inside. The universe isn't a uniform glow, it's a network, and most of the map is darkness. Researchers who study the cosmic web consistently find that voids dominate the universe's volume. In large-scale analyses, the voids can take up the majority of cosmic space, with filaments and clusters occupying far smaller fractions. This matters because it tells us something emotionally sharp. Even if galaxies are astonishingly numerous, they are still arranged like rare lights along threads, surrounded by volumes so large and so quiet that our brains can't naturally visualize them. This creates a deeper mystery. If space is so empty, what does matter even mean at this scale? And that takes us to the next layer, what the universe is actually made of. NASA summarizes the universe's contents in a way that feels almost like a confession. About 5% is normal matter, the atoms that build stars, planets, oceans, and our bodies. About 27% is dark matter, matter we can't see directly, but we detect through gravity. And about 68% is dark energy, the component tied to the universe's accelerated expansion. So when we look at a galaxy in a telescope and think we're seeing the universe, we're seeing a thin surface layer of reality. Normal matter is the part that shines, but most of the universe's substance is invisible to our eyes. Dark matter shapes the cosmic web, acting like an unseen scaffold that helped matter gather into filaments and nodes. And dark energy is tied to the expansion that keeps stretching the cosmic stage beneath everything. But we still haven't answered the most grounded question. Where is the normal matter, the atoms, the stuff that could, in principle, be touched? Because even there, the universe plays another trick. For a long time, astronomers faced a problem. The early universe's light, especially the cosmic microwave background, tells us how much normal matter should exist. But when they added up what they could see in stars and galaxies, a large fraction seemed to be missing. Then fast radio bursts, brief powerful signals from distant galaxies, became a tool to weigh the thin material between galaxies. In 2025, researchers used FRBs to account for the universe's missing ordinary matter and found something astonishing. Most normal matter is not locked inside galaxies. It's spread through the intergalactic medium, a thin, diffuse plasma between galaxies. Reporting on that work, major coverage described a breakdown where the largest share of ordinary matter lies in intergalactic space, with smaller portions in galaxy halos and in the stars and gas within galaxies. So even the atoms, the familiar building blocks of life, are mostly not in the places our eyes go searching. They're out in the dark, floating between the lights. Now we can say the quiet truth plainly. Most of the observable universe is empty in the way our lives understand emptiness. Even where matter exists between galaxies, it is incredibly sparse. ESA offers a visceral reference point when discussing cosmic density, a critical density scale that corresponds to only a few hydrogen atoms per cubic meter, numbers so small they feel unreal compared to air around us. Think about that. In the air, you're breathing right now, particles are packed so tightly that emptiness is not even a concept. In intergalactic space, something can mean only a few atoms in an entire cube of space the size of a large closet. And yet, over billions of years, that thin material still gathered into galaxies, still formed stars, still produced heavy elements, still built the chemistry that let a planet like Earth exist. This is what makes the cosmic web feel almost like cosmic horror. Structure rising out of near nothing. Beauty carved from vacuum. And if you could stand out there, truly stand in intergalactic space, you wouldn't feel wind. You wouldn't hear anything. You wouldn't even feel cold the way our bodies understand it. You'd feel the absence of everything that normally tells you reality is close, and you would understand instantly why the universe can be unimaginably full of galaxies and still be overwhelmingly empty. So what fills this immense volume? Not a smooth fog of stars, but a layered structure, Galaxies by the trillions, many too faint to detect individually, gathered into clusters and walls connected by filaments, the cosmic web, separated by voids that occupy an enormous share of cosmic space, within a universe whose contents are dominated not by visible atoms, but by dark matter and dark energy, and where even the normal matter is often drifting between galaxies, traced by signals like FRBs. This is not a universe filled like a room. It's a universe filled like a coastline at night. Lights along edges, darkness between continents. But here's the strange part. Even after all this, even after counting galaxies, mapping filaments, tracing invisible matter, there is still a hard limit on what we can observe. A boundary made of ancient light, a surface beyond which our telescopes cannot see, not because the universe ends, but because the early universe was once opaque, and the oldest light we can observe becomes a kind of final curtain. That's where we go next, the limits of our vision. We like to believe the universe is open to us, that if we build a stronger telescope, if we sharpen the mirror, if we collect more light, we can keep pushing farther back. But then we reach something unsettling, a glow that surrounds us from every direction. Not a star, not a galaxy, a faint, ancient heat spread across the entire sky. And it doesn't just show us the early universe, it blocks us from going any earlier, because this light is the oldest light we can ever see, and that creates a deeper mystery. If the universe had a beginning, why can't we watch it happen? This glow has a name, the cosmic microwave background, the CMB. It is often called the universe's baby picture because it comes from a time when the cosmos was only about 380,000 years old, a fraction of its current age. And what we detect today is that same light, stretched and cooled by expansion, now arriving as microwaves. It's quiet, it's everywhere, and it is not optional. NASA, missions like COBE and WMAP, and ESA's Planck spacecraft mapped it across the whole sky with astonishing precision. They didn't just confirm it exists, they showed it carries patterns, tiny variations, like fingerprints pressed into the universe's first visible surface. But here's the strange part. The CMB is not light from the beginning. It's light from the moment the universe finally stopped hiding. And that difference matters more than most people realize, because our vision, in cosmology, isn't limited by power. It's limited by physics. To understand why the CMB becomes a boundary, we need to picture the early universe correctly. Not as empty space with scattered stars, but as something closer to a violent, glowing ocean. In those first moments, the universe was hotter than any furnace we can build, and filled with a dense soup of charged particles, electrons, protons, atomic nuclei, packed into a haze of radiation. Light could not travel freely. Every time a photon tried to move forward, it collided, scattered, bounced, changed direction. Not once, not occasionally, constantly. So the universe wasn't dark back then. It was worse than dark. It was blinding and opaque, a cosmic fog made of heat. And this is the key contradiction. If the early universe was full of light, why can't we see it? Because brightness doesn't guarantee visibility. Sometimes brightness becomes the prison. Imagine you're in a bathroom after a hot shower. The room is full of steam, light is everywhere, but nothing is clear. You can turn on the brightest lamp you own, but the steam scatters the light in every direction. You don't see deeper into the room. You see a glowing blur. That steam is what the early universe was like, except the steam was a sea of free electrons and hot plasma, and the lamp was the universe itself. This is why the CMB is so haunting. It's the moment the steam finally thinned. As the universe expanded, it cooled, and eventually, around 380,000 years after the Big Bang, something quiet and irreversible happened. electrons and protons combined into neutral hydrogen atoms. That sounds small, but it was a cosmic collapse of obstacles, because free electrons are excellent at scattering light. Neutral atoms, far less so. So once electrons were mostly locked into atoms, photons stopped being trapped. They could finally travel in long, straight paths. The universe became transparent, and the light released at that moment is what we see today as the cosmic microwave background. That's why ESA describes the CMB as the furthest back in time we can explore using light. Because before that, light doesn't carry clean images. Before that, the universe is a wall of scattering. Not because there was nothing there, but because the universe wouldn't let photons deliver a message intact. When we map the CMB, we are not mapping a physical edge of the universe. We are mapping a surface of last scattering, a spherical shell around us, the place where the photons we receive today last bounced off matter before streaming freely through expanding space. It's a horizon, not a border, a limit of what electromagnetic light can show us, and it creates an unsettling emotional shift. For everything else, stars, galaxies, nebulae, our telescopes collect light that travelled through mostly transparent space. But the CMB is different. It is the earliest moment space became readable, the earliest moment the universe became a window instead of a fog. Picture yourself holding a flashlight in thick fog. You shine it forward, and the beam doesn't pierce the distance. It turns into a pale wall of glow right in front of you. That wall isn't the end of the world. It's the end of what your light can reveal. That is where we stand, with the cosmic microwave background. We're not staring at the end of reality. We're staring at the limit of visibility. The CMB doesn't just block our view. It explains the next era too. After the universe became transparent, it entered a long stretch sometimes called the cosmic dark ages, not because the universe was empty, but because there were no stars yet, no galaxies yet, no bright beacons, just expanding space, cooling gas, and gravity quietly pulling structure together. And the CMB itself holds the earliest trace of those future structures. Cope's measurements revealed tiny variations, subtle differences in the background, early evidence of how matter and energy were distributed when the universe was young, seeds that would later grow into galaxies and clusters. So the CMB is both a photograph and a veil. It shows us the earliest light, and it reminds us we are locked inside the rules of scattering, time, and transparency. This is where cosmology demands restraint. We cannot see earlier than the CMB using light, but that does not allow us to say nothing existed before. It only allows us to say something more careful and more honest. Our method has a horizon. Our evidence has a boundary. Our certainty stops where photons stop carrying clean information. And that's the real lesson of this chapter. Not that the universe hides secrets out of cruelty, but that it reveals them only through certain channels, and only when the physics permits it. So we've found the limit, a glow from when the universe was only hundreds of thousands of years old, still washing over us today, a boundary made of transparency and time. But now the story fractures into a sharper question. If this background is so faint, if its patterns are so subtle, if its variations are so small, how can we possibly measure it with confidence? How do NASA teams, ESA teams, and university researchers separate the universe's oldest signal from all the noise, our galaxy, our instruments, our own motion through space? Because the next part of this journey isn't about imagination, it's about precision. And what comes next is where the universe stops feeling poetic and starts feeling like a high-stakes forensic investigation. We like clean numbers: 13.8 billion years, 93 billion light years. They sound final, like the universe has been measured and sealed. But then the discomfort arrives, because the moment we ask, how sure are we, the story fractures into error bars, calibration debates, hidden biases, and the slow, relentless work of scientists who do not trust a single method, no matter how beautiful it looks. And here's the strange part. Even with all that uncertainty, cosmology is still one of the most precisely measured sciences on Earth. But that precision has a cost, because the sharper our measurements become, the more clearly we can see what doesn't agree. And that creates a bigger problem. When we measure the universe, we're not measuring one thing. We're measuring a chain, a ladder built from light, stepping from nearby stars to nearby galaxies to distant galaxies, until the ladder disappears into the oldest glow the universe can still show, us. And every rung has two kinds of uncertainty. Random noise, the universe is messy, telescopes are limited, samples are finite. Systematic error, the more dangerous kind, when an instrument, a method, or an assumption quietly leans the result in one direction. Scientists don't fear random noise, they fear a hidden tilt, because a hidden tilt doesn't look like an error, it looks like truth. So the real question isn't, do we have uncertainty? The real question is, do we have enough independent ways to catch ourselves when we're wrong? And this is where the story cracks open. Far beyond stars and galaxies, there is a faint, all-sky glow, the cosmic microwave background. It's the afterlight from when the universe first became transparent, when matter cooled enough for light to finally travel freely. NASA and ESA missions have mapped this glow in extraordinary detail, especially ESA's Planck satellite. And Planck didn't just give us a blurry picture, it gave us a kind of cosmic blueprint, a map of tiny temperature ripples that encode the universe's contents and history. From Planck's final results, the age of the universe is pinned down to about 13.8 billion years, with an uncertainty of only tens of millions of years, a breath compared to cosmic time. To feel how sharp that is, if the universe's entire age were compressed into a single calendar year, Planck's uncertainty would be measured in minutes, not days. But then, Planck also predicts an expansion rate today, a value for the Hubble constant that lands around 67 kilometers per second per megaparsec, with a small uncertainty. And that number is where the calm begins to crack, because another set of measurements, built from a completely different approach, keeps landing somewhere else. Now we come closer. We build a distance ladder using objects we can measure step by step. One of the most famous rungs is a type of star called a Cepheid variable, star that brightens and dims in a predictable rhythm. Astronomers use Cepheids to measure distances to galaxies close enough that we can still resolve individual stars. Then they connect that rung to a brighter signal. Type Ia supernovae, stellar explosions so luminous they can be seen across vast fractions of the observable universe. This is the approach used by the SHOES team, a long-running collaboration led by astronomers including Adam Rees, building on decades of work in observational cosmology. Their latest analyses keep pointing to a faster expansion rate today, around 73 kilometers per second per megaparsec, with roughly 1 to 2% uncertainty. So now we have two clocks, two rulers, two methods that should, if we understand everything correctly, converge. But they don't, and that mismatch has a name, the Hubble tension. Not a slogan, a real, quantified disagreement between early universe predictions and late universe measurements, and that is not the whole story, because the universe offers more ways to measure itself, ways that don't rely on Cepheids at all. Long before galaxies existed, the early universe was a hot plasma, a glowing dense sea where matter and light were chained together. Pressure waves moved through that plasma like sound through air. When the universe cooled and became transparent, those waves froze in place, leaving a preferred separation scale imprinted into the large-scale structure of the cosmos. This is baryon acoustic oscillations, BAO, a standard ruler written into how galaxies cluster. Modern surveys, especially the Dark Energy Spectroscopic Instrument, DESI, and Sloan Digital Sky Survey programs, measure BAO using millions of galaxies and quasars, turning the universe into a statistical experiment of immense precision. Here's the unsettling beauty. BAO doesn't care about Cepheids. It doesn't care about supernova brightness calibration in the same way. It's a geometric imprint, a ruler. And when BAO is combined with cosmic microwave background measurements, the results strongly reinforce the same overall picture of cosmic history, while still keeping the Hubble tension alive as a stubborn mismatch that won't evaporate easily. So now, instead of one ladder, we have multiple independent scaffolds. And yet the disagreement remains, which means either there's a hidden systematic error somewhere, or something in the model is incomplete. Scientists do not get to choose which one is true. They have to earn it. Now we use gravity as a yardstick. Time delay, gravitational lensing. Sometimes a distant quasar is split into multiple images by a massive galaxy in the foreground. The light takes different paths, so it arrives at different times. Measure those time delays, model the lens mass carefully, and you can infer cosmic distances and the expansion rate. The H0Li-Cow program achieved about a 2.4% measurement of the Hubble constant from lensed quasars, finding a value consistent with the faster local expansion measurements. But then the next layer of realism arrives. Other collaborations like TD Cosmo have spent years dissecting how sensitive lensing results are to assumptions about galaxy mass profiles and systematics, showing exactly why this is hard and why careful uncertainty work matters. This is what scientific honesty looks like, not announcing certainty, but mapping every place certainty could collapse. Gravitational waves, standard sirens, and then something even more alien. A neutron-star merger sends out gravitational waves. Those waves carry distance information directly, without the traditional distance ladder. In 2017, the neutron-star merger GW170817 opened this door, giving an independent estimate of the expansion rate, still with large uncertainty, but fundamentally different in method. This isn't the clean final answer, it's another independent witness. And in a universe this large, we need witnesses. Imagine this. We're in a dark city at night, and we're trying to measure the size of the city, but we can't see the whole thing. So we do something careful. We measure using the spacing of streetlights, the timing of distant sirens, the pattern of neighborhoods, and the way echoes bounce off far buildings. Each method has blind spots. Each method has noise. But here's what changes everything. If all these methods, built from different physics, keep pointing to the same overall scale, then the city is real, even if our map isn't perfect. That's how cosmology works. Not one miracle measurement, but converging constraints from light, from matter, from gravity. And this is why the scale of the observable universe is not a casual guess. It's a structure supported by multiple beams. But the universe had one more twist. Because the more precisely we measure, the more we discover a deeper question. Which beam is bending? Even with tensions and debates, there are pillars that hold. The universe is about 13.8 billion years old. This number isn't floating on a single paper. It's supported by precise cosmic microwave background measurements and consistent cosmological modelling across multiple datasets. The early universe imprint is measured with extreme precision. Planck's parameter constraints, like the characteristic BAO-related scale, are pinned down tightly, which is why the standard model is so predictive. Large-scale measurements reinforce each other. Modern galaxy surveys and weak lensing programs, DES KIDS, produce cosmological constraints that broadly align with a consistent large-scale picture of the universe, even while details remain under active scrutiny. These are not fragile claims. They've survived cross-examination. And now we speak the careful truth. The Hubble constant is still contested. Early universe predictions from Planck sit near 67, while late universe measurements like Schu's sit near 73. This isn't a rounding error. It's a real disagreement, large enough that scientists treat it as a major open problem in modern cosmology. Systematics can hide inside perfection, Cepheid calibration, dust, population effects, supernova standardization, selection bias, lens modeling assumptions. Even the cleanest looking numbers can be quietly skewed, and scientists build entire careers around finding those skews. Because if the universe is forcing disagreement, it's either because we made a mistake or because we discovered a crack in the model, and neither outcome is comfortable. And this is where you come in. Because when we say uncertainty, we don't mean we're lost. We mean we are doing something almost impossible. We are measuring a reality so vast our minds were not built to hold it. And yet, with fragile instruments on a small planet, we can estimate the universe's age to within a fraction of a percent. That should feel unsettling, not because it's wrong, but because it's real. So why is there consensus at all? Because the big picture is constrained from many directions at once. The cosmic microwave background pins down the early conditions. BAO provides a ruler across cosmic time. Supernovae map how expansion changed over billions of years. Weak lensing measures how matter clumps and curves light. Lensing time delays and gravitational waves offer independent routes to distance. When these different tools, built on different physics, paint the same broad architecture, the architecture becomes difficult to deny. The details still matter. The tension still matters, but the foundation holds. And now we reach the edge of this chapter's truth. Our measurements are precise enough to map our observable horizon, but not powerful enough to turn that horizon into a claim about everything. And that raises another question. So here is the final, quiet twist. Even if our measurements became perfect tomorrow, even if every tension dissolved, we would still face a boundary that no instrument can outmuscle. Because precision does not grant permission, it only strengthens what we can honestly say. Which means the next step is not about bigger numbers. It's about a deeper restraint. What is the observable universe? And what is it not? Because observable is not a synonym for total, and that distinction changes everything. We keep saying it like it's harmless. Observable universe. It sounds complete. It sounds like a container we've already measured, a cosmic room we've already mapped. But that word, observable, is not a badge of mastery. It's a confession. Because the moment we say observable, we admit something quietly terrifying. There is a universe, and then there is the part the universe has allowed us to see. And the difference between those two is where human certainty begins to fracture. But then the real discomfort appears. If our telescopes can see nearly to the beginning of time, why can't we see everything? Why does the universe still keep a portion of itself hidden, not behind distance, but behind the rules of reality itself? And to understand that, we have to accept a boundary that isn't a wall. It's something far stranger. Let's slow down and name the rule clearly. The observable universe is not what's out there. It is what can reach us. It's a region defined by the simple physics of light and time, not by the ambition of our technology. Britannica describes it as a region we can actually, or theoretically, observe, and separates it from the entirety of the universe, the whole cosmic system of matter and energy. NASA says it even more bluntly. We can estimate the size of the observable universe, but science has no reliable estimate of the actual size of the entire universe. That sentence should land like a heavy object, because it means something that quietly rearranges our place in reality. We do not live inside the universe we see. We live inside a horizon of information, and beyond that horizon, cosmology becomes a discipline of restraint. Here's where our everyday intuition collapses. When we hear limit, we imagine an edge, a cliff, a fence, a final line. But the observable universe isn't a boundary in space. It's a boundary in causality, in what can ever affect us, ever reach us, ever become part of our evidence. Imagine this. You're standing on a dark beach at night. A lighthouse flashes far away through thick fog. You don't doubt the ocean continues beyond what you can see. You don't claim there's a wall where the fog becomes opaque. You simply admit the truth. Your view has limits, even if the world does not. That's what observable means in cosmology. Not the universe ends here, but our evidence ends here. And this creates a bigger problem, because it means two things can be true at the same time. The observable universe can be measured with breathtaking precision, and the entire universe can remain fundamentally unknown in size. The deepest reason we cannot just look farther. There is a hard ceiling on what light can show us. The European Space Agency describes the cosmic microwave background, the CMB, as the farthest and oldest light any telescope can detect, and explains why. Before that moment, the universe was effectively opaque, so light couldn't travel freely to us. So even if we build a telescope the size of a planet, even if we place it in perfect darkness, even if we sharpen its eyes beyond anything humanity has ever imagined, we still collide with the same cosmic rule. There is a time before the universe was transparent, and beyond that time, there is no light to collect. That's why the line between observable and total is not a matter of effort, it's a matter of physics. And then it gets stranger, because the universe doesn't just hide beyond the CMB, it also hides beyond the future. Over cosmic time, more and more galaxies drift beyond our horizon, not because they move through space like rockets, but because space itself expands. So the observable universe is not only limited, it is also temporary in what it contains. And that raises another question. If our evidence is constrained, what does science do with the unknown? This is where cosmology becomes a discipline of honesty. Science does not fill the darkness with storytelling. Science separates two categories with a hard line. 1. What we can measure. We can measure the universe's age to about 13.8 billion years, using evidence like the microwave background and the expansion history. We can estimate the size of the observable universe as roughly 90+ billion light-years across, an immense measured horizon of reachable information. And we can map patterns in the relic light itself, a sky-wide fossil record of early conditions. These are not guesses, these are measurements chained to evidence. 2. What we cannot claim, but the moment we ask, how big is the entire universe? We step beyond what observation can guarantee. NASA says directly that we don't have a reliable estimate of the actual size of the whole universe, and that we don't actually know whether it's finite or infinite. That isn't weakness, that is scientific integrity. Because in cosmology, the temptation is always the same, to mistake a map for the territory, to confuse a horizon with a border, to treat the visible as the total, but the visible is not the total, not in space, not in time, not in meaning. And if you ever feel disappointed by that, if you feel the urge to demand a final answer, remember what this restraint really protects. It protects reality from our certainty, because the universe is not obligated to be fully legible to the human mind. What comes next challenged everything, not because the numbers are wrong, but because the humility is correct. So here is the quiet conclusion of this passage. Observable does not mean small. It does not mean complete. It means reachable by light, by time, by causality. And beyond that, science does not pretend. It waits. It measures. It refuses to manufacture certainty where the universe has not provided evidence. But this is where everything changes, because once we accept that the cosmos we can see is only a horizon, once we accept that our map is only a fragment, a deeper question replaces the one we thought we were asking. Inside this measured bubble, where exactly are we? Not just in space, but in structure, in context, in meaning. And that's when the real story tightens its grip, because our position in this scale is not special, and yet it may be the most meaningful fact we ever discover. We like to believe we know where we are. We can point to a street, a city, a country. But in the universe, our address doesn't just stretch. It fractures into layers, each one larger than the last, until the idea of here starts to collapse. Because the deeper we go, the stranger it gets. We are not sitting at the center of anything. We are not standing on a pedestal. We are drifting inside a structure so vast, it makes location feel like a fragile human invention. And yet, this is where everything changes, because even from this non-special place, we have learned to measure the darkness. But that raises another question. If we are not central, why does our viewpoint matter at all? Picture this. Imagine writing your home address on an envelope. You don't start with the planet. You start with something small, your house number, then the street, then the city, then the country. The universe works the same way, except every line on the cosmic envelope is unimaginably larger than the last. So let's write it together, not with mythology, not with comfort, with what astronomers can actually measure. Our first line is simple, Earth, then the next line, the solar system, our small circle of light around an ordinary star. But the moment we add the next line, we enter a scale that no human brain was built to hold. The Milky Way. NASA describes our sun as sitting in a small partial spiral arm called the Orion Arm, or Orion Spur, between the Sagittarius and Perseus arms. That sentence sounds calm, but it hides a truth that should feel unsettling. We are not near the center. We live out in the galactic suburbs, about 25,000 light-years from the Milky Way's center, according to NASA's education resources. And a light-year is already a warning label. It's distance written in time. So our neighborhood is not measured in miles or kilometers. It's measured in years of light traveling through cold, vacuum. Here's the strange part. Even our galaxy is not a static place we sit inside. We are moving. NASA states our solar system orbits the galaxy's center at about 15,000 miles per hour, 828,000 kilometers per hour, and takes roughly 230 million years to complete one orbit. Let's translate that into something we can feel. At 15,000 miles per hour, 828,000 kilometers per hour, we could cross the United States in seconds. We could circle Earth again and again before the day even finishes. But even at that speed, one single lap around the Milky Way takes longer than almost all complex life has existed on Earth. 230 million years ago, Earth didn't have cities. It didn't have languages. It didn't have recorded memory. It had oceans, forests, and creatures that belonged to a different planet in spirit. So when we say, we are located in the Milky Way, what we really mean is, we are riding a river of stars, inside a rotating storm, on a timescale that makes human history vanish. And this wasn't the only one, because the Milky Way is not alone. If we zoom out, the Milky Way stops looking like the universe. It starts looking like one lantern in a field of lanterns. NASA describes the local group as a collection of over 50 galaxies, including the Milky Way and its closest neighbors like Andromeda. And NASA's materials highlight something quietly important. In our local neighborhood, the biggest names are familiar: the Milky Way, Andromeda, and the Triangulum Galaxy. This is the layer where the universe begins to feel crowded, but even here, the crowd is mostly emptiness. Galaxies are not packed like buildings. They are scattered like isolated islands in a black ocean, separated by distances so large that even light needs millions of years to cross between them. So, our position is already humbling. We are not at the center of the Milky Way. The Milky Way is not at the center of the local group. And beyond the local group, the structure grows again. Now we step into a scale that sounds almost fictional, except it isn't. It's mapped using real measurements, galaxy motions, gravitational flows, and the way matter pulls matter across space. In 2014, astronomers defined a vast structure they called Laniakea, often described as our home supercluster. NASA's Astronomy picture of the day explains that Laniakea includes our Milky Way, the local group, and even the nearby Virgo cluster of galaxies. And according to a University of Hawaii linked release describing the same work, Laniakea spans about 500 million light-years and contains on the order of 100,000 galaxies. 500 million light-years. That number is not just big, it's emotionally violent, because when we say light-year, we are saying even light, nature's fastest messenger, needs 500 million years to cross this home. 500 million years ago on Earth, there were no humans, no cities, no written language. Complex life was still experimenting with shapes in the sea, and yet that is the timescale of just one of the structures we belong to. But then, we learn something colder. Even superclusters are not the final container. They are strands in something larger. NASA describes the universe on the largest scales as an architecture of galaxy groups, clusters, filaments, and vast empty voids. A kind of structure sometimes called the large-scale structure. So our true position is not a point, it's a nesting, a chain of belonging, Earth, solar system, Milky Way, local group, Laniakea, the cosmic web. And if that feels like it should make us insignificant, that reaction makes sense, but it's not the whole story. Because not special is not the same as meaningless. There is a temptation, ancient and human, to believe the universe must be arranged around us. But science spent centuries shattering that instinct. Copernicus removed Earth from the center of the solar system. Astronomers showed our sun is one star among many. Edwin Hubble's work revealed the Milky Way as one galaxy among countless others. Again and again, the universe refuses to place us on a throne. And this creates a deeper mystery. If we are not central, how did we become aware of the whole? Here is the uncomfortable truth we often avoid. Our bodies are small. Our lifetimes are brief. Our planet is a thin film of life on a rocky sphere. And yet, from this unremarkable position, we have built instruments that read the universe like a forensic scene. We traced our place in the Milky Way's spiral structure. We measured our orbit around the galactic center. We mapped our neighborhood of galaxies. We identified the supercluster we drift inside. We did this without being large. We did it by being curious. And that is the emotional inversion at the heart of cosmology. The universe does not give meaning by placing us at the center. We create meaning by learning where the center is not. One possibility remained. Maybe our importance was never about location. Maybe it was about perception. And now, just once, place yourself inside the scale. Imagine you could step outside at night and see the Milky Way not as a pale band, but as a whole galaxy, all at once, spiral arms like faint smoke rotating in silence. You would not feel central, you would feel something sharper, that being alive here is statistically rare and intellectually explosive, because we are matter that learned to look back at itself. So in this layer of the story, we've located ourselves, not special in position, but extraordinary in what we can understand. But the universe has one more twist, because even after mapping our cosmic address, we still haven't answered the quietest, heaviest question. What does it mean to live inside a horizon we can never outgrow? Because the next step isn't about where we are, it's about what we can never reach. And that's where our final answer begins. We keep returning to one impossible claim, that the observable universe is almost 93 billion light-years across, a number so large it doesn't feel like measurement, it feels like myth. And yet, this number is not poetry, it's a consequence of something we don't instinctively accept, because our minds were never built for it. Space itself has been expanding the entire time light has been travelling. So the scale isn't an illusion, it's physics doing what physics does, quietly, relentlessly, while we lived our entire human story inside a fraction of a second on the cosmic clock. But then, we reach the uncomfortable edge, because even if we understand the number, we still have to face what it implies. We will never see everything, not because we lack technology, because we lack time. And time is the one resource the universe does not give back. When we say observable universe, we are not naming the whole universe, we are naming our horizon of evidence, the farthest distance from which light has had enough time to reach us since the universe became transparent, since the early cosmos cooled enough for light to finally travel freely. That is the key, not distance, time. Light is not a flashlight beam, light is a messenger, and our observable universe is made from the messages that had time to arrive. So this final chapter is not about claiming what lies beyond, it's about staying honest about what we can measure and what we cannot, and still finding meaning inside that honesty. Here's the tension we've been carrying through this entire journey. If the universe is about 13.8 billion years old, then common sense whispers, how can we see anything farther than 13.8 billion light-years away? It sounds like the story should stop there. But common sense assumes space is fixed. It assumes light crosses a frozen stage. Except it doesn't. Space has been stretching, while light has been moving. So the farthest light we receive today started its journey when the universe was young, then travelled through a cosmos that kept expanding beneath it, like a road lengthening while the traveller is still walking. This is why the observable universe can have a radius of roughly 46 billion light-years, even though the universe is younger than that number. That isn't a trick, it's the geometry of an expanding cosmos, and this changes everything. Because it means the observable universe is not a sphere we could reach if we travelled long enough. It is not a border, it is a horizon drawn by the speed of light, the age of the universe, and the expansion of space. A horizon that is not a wall, but still, in a very real way, a limit. Imagine this. We're standing in a city at night, and we send a friend a letter. They start walking toward us with that letter in their hands, but while they walk, the city itself begins expanding. Every street lengthens, every block stretches. Our friend is still walking at the same speed, the letter is still travelling, but the distance the letter must cross keeps growing under their feet, so when the letter finally arrives, it doesn't prove the city was always that large. It proves the city grew while the message was in transit. That is the observable universe. A message, light, crossing a world, space-time, that refused to stay still. And the fact that the message arrived at all is the reason we can measure anything. So what does our measurement actually mean? It means we can reconstruct a consistent story. The universe had a beginning hot and dense enough to erase ordinary structures. It expanded and cooled. Eventually it became transparent, allowing light to travel freely. That ancient light still exists, stretched into the faint background glow we detect today. Meanwhile, the space between everything continued to expand. The observable universe is vast because the universe has had time, and because space has had a history. When we say 93 billion light-years across, We're not describing the path a photon travelled in a straight line through a static cosmos. We're describing the present-day scale of the region of space that produced the light we can receive. That distinction matters because it keeps our minds from committing the most common mistake. Thinking the observable universe is the same thing as the entire universe. It isn't. It's the part of reality whose signals have reached us. And this is where restraint becomes an act of intelligence. Because when we stand at the edge of what we can see, the universe invites a dangerous temptation to fill the darkness with certainty. Science refuses that temptation, not out of fear, out of discipline. We stay with what the evidence allows. We do not pretend our horizon is the whole ocean. And right here, there is a truth that becomes hard to say out loud. You are alive inside a boundary made of light, not a prison, a horizon, a limit that doesn't care about our ambitions, a limit that doesn't hate us. It simply exists. And within it, everything we've ever loved has happened. Every human voice, every war and reconciliation, every song whispered into the dark, every civilization rising like fireflies and fading again, all of it inside a small, thin slice of cosmic time. That should feel insignificant, except it doesn't, because awareness changes the weight of scale. If the universe is vast and we are small, then our thoughts are not less meaningful, they are more improbable. When we look out into the cosmos, we are not looking at far away. We are looking at long ago. A nearby star is a recent message. A distant galaxy is an ancient one. And the farthest light we can ever detect is a message from the early universe itself, arriving like a final postcard from the edge of our visible history. That's why observable is a deeper word than it sounds. It means the universe is not just a place, it is a timeline, and our horizon is not drawn by distance alone, it's drawn by time, by how long reality has existed, in a form that allows information to travel. So no matter how advanced we become, we will always live inside a past we can never fully escape. Our telescopes don't just magnify space, they excavate time. Now we arrive at the final quiet answer. The observable universe is vast because space has expanded over time. Its scale is not an illusion. It is a measurable consequence of physics, and we do not see everything, only what light and time allow. That is the honest boundary of our knowledge. But here is what that boundary contains. Within this limited horizon, every atom of Earth, assembled from ancient stars, recycled through cosmic violence, shaped into oceans and forests and bones. Within this limited horizon, every thought ever formed, every mind that has ever looked up and felt the weight of the night sky pressing back. Within this limited horizon, every question ever asked, not just the scientific ones, the human ones. Where are we? What is real? Does anything we do matter? And the universe answers in the only way it knows how, not with comfort, with clarity. It tells us we are not the center, but we are not outside the story. We are inside the universe, made of it, thinking about it, and that may be one of the rarest things matter can do. So here is the ending, spoken softly because the truth doesn't need volume. We live inside a horizon, not because reality ends, but because time does not stretch far enough for every message to arrive. Beyond our horizon, there may be more universe, or not. Science does not pretend to know. And that restraint is not a limitation of imagination, it is respect for evidence. But even if we never see beyond, even if our entire species lasts only a brief flare on a drifting planet, we have already done something astonishing. We have learned to measure the darkness. We have learned to read the oldest light. We have learned that the universe is vast, not as a metaphor, but as a fact. And then we did something even stranger. We cared. We turned scale into meaning. We looked into a cosmos that does not need us. and we still chose to understand it. Because knowledge is not a product of size, it is a product of curiosity. And curiosity is how the universe, through us, becomes aware of itself. So when we say the observable universe, we are not naming a cage. We are naming a shared horizon, the farthest edge of what our existence can confirm. And inside that horizon, every atom of Earth, every thought ever formed, every question ever asked, all of it held for a moment against an ocean of time. And the most human truth of all is this: the universe is unimaginably large, but meaning is something we build quietly, together, inside the light we are given.